Simulation is an imitation of chance behavior. We've done several of these already this year. We just didn't call it a simulation. For example, one of the very first days of school when we did the hiring discrimination activity about the airline and we pulled the beads out of the bag, that was a simulation of their lottery process. We've also done a simulation when we did the distracted driving activity, and we did a simulation the other day when we did the whose book is it anyway activity. All of these are simulations. They're just, you take scenarios that have in some type of chance behavior involved and you create a way to simulate it. And the reason we do this is because it would be very expensive to, or sometimes impossible, to simulate the exact situation, to repeat that exact situation over and over and over again so that we could analyze the probability. Or sometimes it's even dangerous. With the distracted driving, they simulated driving with a driving simulator. We simulated it with playing cards because we didn't have access to their simulator. They used a simulator because it would be dangerous and somewhat unethical to put people in this situation of really driving distractedly. So simulations allow us to analyze the probabilities and the outcomes in a more affordable and more simple environment. So what steps do we do? We always have 4 steps for everything, and our 4 steps here for a simulation are the same as our 4 steps when we are solving a problem, like our normal distribution problems: state, plan, do, conclude. So let's take our whose book is this anyway activity from class. We didn't do it on Friday, we did it on Tuesday, but we'll take it anyway. And here are our 4 steps. So state, when the 4 students mix up their AP book, what is the probability that each one will randomly choose a book and not end up with their own? So what is the probability? Each student will end up with an incorrect book. So that's our state. Then we have to plan. And here we're just going to describe what it is that we did. We did on 4 equally sized index cards. Write the numbers 1, 2, 3, 4. Shuffle the cards and lay them down one at a time in a row. If the number on the card matches the position in the row, that student received the correct book. Count the number of students who received the correct book. And there's our plan. We just basically described what we did in the simulation. So after the plan comes the do step. And for the do step, you just want to perform as many repetitions of the simulation as possible. For us in class, we each did it a few times, but because we each did it, that gave us many more repetitions. And the further I went through the day and the more classes I did it with, the more repetitions I had. So for the do step, it's perform as many as possible. I'm sure that you're thinking, well, how are we going to perform as many repetitions on a test as possible? But for a test or an assignment, what I will ask you to do is perform 3 repetitions or perform 5 repetitions. I will give you a specific number. But in general, the do step is to perform as many repetitions of your simulation as possible. The more information you have and the more time you do it, the more you can rely on the probability and the answers that you get. And then, as always, our final step is to conclude. Okay, we want to answer the question. We're going to use the results of the simulation to answer the question. Something you always want to remember when you are concluding is to use the word approximately. Kind of like how we had to use the word predicted in the last chapter when talking about our answers, we want to use the word approximately here. Okay, we never want to say that a probability is 18 over 100, for example. It would be better to say that it is approximately, because that's all we can do with a simulation is get the approximation. I don't have enough evidence to say that that's what exactly would happen. So kind of like how we had to say estimated, predicted, etc. in Chapter 3 when talking about the least squared regression line, because it's not exactly what would happen. Here we have to say approximately because we don't know that the real result will be exactly the probability that we get. Some simulations use playing cards. We've used those before. Some use beads. Anything that will produce a random result or follows the rules of probability and randomness will work. And one of the main things that does that statisticians rely on a lot, is a table of random digits. However, I have some tips for you if you decide to use a table of random digits. For one, make sure that you have equal sized labels. For example, if you're labeling something from 1 to 500, it needs to be from 001 to 500. Okay, equal sized labels when using your table of random digits. Otherwise, when I see a number like 145, how do I know it's not a 1, a 4, and a 5 versus 145 or a 1 and 45 or a 14 and a 5? So I need to make sure that I'm using equal sized numbers. Also, I want to actually explain what I'm doing with any extra numbers. For example, if I'm only using the numbers from 1 to 500, what about if I came to number 784? What would I do with that? And in this case, I would ignore it and skip it, and I need to specify that. So be very specific about how you will use your table of random digits. Are you using replacement? Are you not using replacement? Okay, that's another one. So just be very specific about how you are going to use the table, and you will be fine. But these are 3 things to think about when describing how you are using the table of random digits. Do you have equal size numbers? Are you explaining what you are doing with the extra numbers, and have you decided whether or not you are going to use replacement? So, for example, let's look at an example. Suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper and mix them up in a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggests that I should stratify by class. I agree, and we decide that it would be appropriate to select 4 seniors and 2 juniors. However, since I already mixed up the names, I don't want to go through and separate them all. So instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names. So design and carry out a simulation using Table D to estimate the probability that you must draw 8 or more names to get 4 seniors and 2 juniors. So I could do a couple different things with this. I could cut up 90 equally sized pieces of paper, label them 6 of them with an S and 30 of them with a J, and put them all in a bag, and then draw out until I get 4 of the S's and 2 of the J's. However, that's a lot of work to cut up all those pieces of paper. So I could use beads. What if I used, 60 red beads and 30 blue beads, and I pulled them out until I got 4 red beads and 2 blue beads? However, if I don't have beads, I may need something else. So we're going to actually use Table D, our random number table, with this one, just to show you an example of how we can. Typically on a test, if I ask you to use a simulation, I'm going to ask you to do it with Table D because you're not going to have beads or slips of paper or anything with you on the test. So it's good to know how to use Table D. So if I'm looking at Table D in the back of the book, and I start with line 101, I get the numbers 19, 22, 39, 50, 34, 5, 75, 62, 87, and 13. And we'll just hold on to those for right now. Those would be the first numbers we would draw. But if we're going to design and carry out a simulation, there's a couple of steps we need to do before we get to that part. So the first things first would be state. What is the probability that it takes 8 or more selections to get my 4 seniors and 2 juniors? So then comes the plan. Okay, one thing I want to do is I'm going to label my seniors 0, 1 through 60, and I wouldn't have to do the seniors first. I could have done the juniors first. Totally up to you. And juniors, okay, because there are 30 of them, that would be 6, 1 through 9, 0, which means numbers 0, 0, and 9, 1 through 9, 9 will be ignored or skipped. Then I'm going to use pairs of numbers from Table D, which we've already gotten. Starting at row 101. I need to also say something about the fact that I'm not using replacement. Okay, so this is sampling without replacement. I will count how many numbers it takes to get 4 seniors and 2 juniors. Okay, so then I have to go actually do the step. I'm only going to do it one time on paper. So if I'm going to do this once, 19 is a senior, 22 is a senior, 39 is a senior, 50 would be a senior. So there are my 4 seniors right there. But 34 is a senior, so I don't need it. 5 is a senior, so I don't need it. Then I get to 75, which is a junior, and 62, which is also a junior. So right there are my four seniors and 2 juniors, and it took me 1, 2, 3, 4, 5, 6, 7, 8 numbers exactly to get it. Okay, so in the do step, you're only showing me this one time or 2 times or 3 times, but if I wanted the actual simulation, I would need to do this many different times. Okay, so if we were each doing it in class and everybody started on a different row of the random number table, or I used the calculator or a computer program and started with different parts of a random number table each time. And in fact, I did this on the calculator. And out of 50 trials, 11 of them, it took 8 or more. So then my conclusion would say, in the simulation, 11 of the 50 trials required 8 or more selections to get 4 seniors and 2 juniors. So the probability that it takes 8 or more selections is approximately, there's my magic word, approximately 0.22. So that is how we run a simulation with a random number table.